Welcome to Sleepy Astronomy. I'm so glad you've joined me tonight. Allow your body to unwind and your thoughts to float softly through space. Beyond the light of our own sun, countless stars shine, each with their own family of worlds. Tonight, we'll visit some of these faraway planets, mysterious and beautiful, drifting silently through their distant orbits. These are the exoplanets, the hidden gems of our galaxy. In the vast tapestry of the cosmos, the idea of planets beyond our own solar system once belonged to the realm of speculation. For most of human history, stars were thought of as distant lights, eternal and unchanging. But with the advance of science came the courage to ask deeper questions. Could those distant stars also host planets? Could some of those planets cradle life? The search began in earnest in the late 20th century. In 1995, astronomers Michel Mayor and Didier Queloz made a breakthrough. They found a planet orbiting another star. This exoplanet, called 51 Pegasi b, circled its star more closely than Mercury orbits our Sun. It was a gas giant, a world unlike Earth in almost every way. Yet it proved beyond doubt that planets do exist around other stars. Since then, the field of exoplanet discovery has grown rapidly. Today, more than 5,000 exoplanets are known. Each has been found using one of several key methods. One of the most powerful techniques is the transit method. When a planet passes, or transits, in front of its star, from our point of view, the starlight dims ever so slightly. By carefully observing this dip in brightness, astronomers can detect the planet and even estimate its size. Another valuable approach is the radial velocity method. As a planet orbits its star, its gravity causes the star to wobble very slightly. This wobble changes the color of the starlight, shifting it toward red or blue as the star moves away or towards us. With precise instruments, these tiny shifts can be measured, revealing the presence of a planet. A third method, more challenging but deeply rewarding when successful, is direct imaging. In this case, telescopes capture pictures of planets by blocking out the intense light of the host star. Though rare due to the difficulty of seeing planets so close to such bright stars, this technique provides a more direct glimpse of alien worlds. With these discoveries comes a natural question: could any of these planets support life? Astrobiologists approach this question with caution and care. They look for signs that a planet might be habitable. It begins with location. A planet must lie within the habitable zone of its star, sometimes called the Goldilocks zone. Here, temperatures are just right, not too hot and not too cold, for liquid water to exist on the surface. Water, as far as we know, is essential for life. But location is just the beginning. A truly habitable world must possess more. It should have a stable atmosphere, one that can regulate temperature and shield the surface from radiation. It may need magnetic fields to protect it from stellar winds. Surface conditions must remain steady for long periods, allowing life the time it needs to arise and evolve. To probe deeper, scientists search for biosignatures, indicators that life might be present or might have once existed. These can include gases like oxygen and methane, especially when found together in a planet's atmosphere. On Earth, this chemical combination is maintained by living organisms. Discovering such patterns elsewhere would be a tantalizing clue. Today, instruments like the James Webb Space Telescope and the upcoming Ariel mission are designed to study the light that filters through the atmospheres of distant planets. This light carries the fingerprints of gases, making it possible to detect potential biosignatures through spectroscopy. The search for habitable worlds is not just a scientific endeavor. It's a profoundly human one. It touches a deep part of ourselves, the part that looks up into the night and wonders whether we are alone. Each new exoplanet brings us closer to understanding our place in the universe. It reminds us that our world, however small, is part of something larger, older, and infinitely more mysterious. 500 light-years from Earth, in the faint star field of the Cygnus constellation, lies a planet that changed the way we imagine our place in the cosmos. Kepler 186f, the first Earth-sized world discovered orbiting within the habitable zone of another star. It is close enough in size to our own planet to invite comparisons, yet distant and alien enough to stir our deepest curiosity. The star it orbits, Kepler 186, is a red dwarf. Smaller and cooler than our Sun, it gives off far less light. Even though Kepler 186f sits within what we call the habitable zone, that delicate band around a star where conditions might allow liquid water to pool on a surface, the world receives only about a third of the light we enjoy on Earth. A dim, ruddy twilight would bathe its surface, if the planet is not enshrouded in thick cloud or ice. Still, its presence in the habitable zone marks it as something special. The discovery came through the transit method, where astronomers observe the slight, regular dimming of a star as a planet passes in front of it. From those subtle dips in brightness and repeated passes, they deduce the planet's size and orbit. In the case of Kepler 186f, the data revealed a rocky world, one with a radius just slightly larger than Earth's. What we don't yet know is the composition of its atmosphere, or even whether there is one. But the potential is there. With the right mix of gases, greenhouse effects could warm its surface enough for water to remain liquid. And where there is water, there may be life. If Kepler 186f has seas, perhaps nature has followed a similar script. But its red dwarf sun brings challenges. Red dwarfs are volatile, especially in their youth, prone to violent stellar flares and radiation bursts. Such storms can strip away an atmosphere or bathe the surface in ultraviolet light. Kepler 186 appears quieter than many of its kind, yet it is an open question whether its companion planet could preserve an atmosphere thick enough to shield life. Then there is the question of orbit. Planets so close to dim stars often become tidally locked, with one hemisphere always facing the star, bathed in eternal twilight, and the other in perpetual cold. Such a world might host violent temperature gradients, with fierce winds moving heat from one side to the other. Or perhaps, like some models suggest, a thick enough atmosphere could redistribute warmth and leave a temperate zone in between, a ring of twilight where conditions are just right. Kepler 186f set in motion a new era of exploration. Before its discovery, we found gas giants and super-Earths, often hot and forbidding. But this was something different, a small, rocky planet in the habitable zone. It showed us that Earth-like worlds could be common, that our planet isn't a cosmic rarity, but perhaps one of many scattered across the galaxy. We cannot yet see its surface, but with future telescopes, that may change. Instruments like the James Webb Space Telescope and its successors may reveal the fingerprints of atmosphere, signs of clouds, or even gases like oxygen or methane that, on Earth, are hallmarks of biology. To glimpse such signals through the void would be a milestone in the search for life. Until then, Kepler 186f remains distant and silent, a quiet cousin of Earth, orbiting a crimson star beneath skies we cannot yet touch. But its discovery brought us closer to the idea that, somewhere out there, the conditions for life may not be unique to us, that the story of life on Earth might be one chapter in a much larger cosmic tale. 40 light-years from Earth, in the direction of the constellation Aquarius, lies a miniature planetary system that has captivated astronomers since its discovery. Known as TRAPPIST-1, it is unlike anything we have seen before. Its host star is a small, cool red dwarf, only about 9% the mass of our Sun. Around this faint ember of a star orbits 7 planets, every one of them roughly the size of Earth. They form a planetary ballet, locked together in a delicate gravitational rhythm. The TRAPPIST-1 system is both compact and orderly. All 7 planets orbit closer to their star than Mercury does to the Sun. Yet, despite their tight spacing, the gravitational interactions between them create a stable resonance chain. This orbital harmony allows us to calculate their masses and compositions with striking accuracy. It also gives scientists the rare chance to see how planets evolve side by side under similar conditions. 3 of these 7 worlds lie in the so-called habitable zone, the region where temperatures might allow liquid water to exist on the surface. It is in this zone that the alchemy of life, as we understand it, could begin. TRAPPIST-1e, in particular, has emerged as a strong candidate for further study. It appears to be rocky, with an atmosphere that may be dense enough to support surface oceans, shield the surface from solar radiation, and regulate its climate through greenhouse effects. The planets of TRAPPIST-1 are likely tidally locked, meaning the same side always faces their host star, much like the Moon always shows one face to Earth. This results in permanent day on one hemisphere and endless night on the other. It may sound like a hostile environment, but tide locking doesn't necessarily exclude habitability. The twilight regions between the day and night sides, the so-called terminators, might provide stable environments with moderate temperatures, where water could pool and biology might thrive. One of the most tantalizing possibilities is that some of these planets may harbor subsurface oceans beneath icy shells, similar to the moons Europa and Enceladus in our own solar system. If so, geothermal heat and perhaps even chemical energy from the interior could sustain life entirely independent of sunlight. These hidden oceans may be dark, cold, and silent, but not necessarily dead. They offer a powerful reminder that life, if it exists elsewhere in the cosmos, may flourish in forms and places we have yet to imagine. The TRAPPIST-1 system is also a dream for atmospheric science. Because the planets pass in front of their star from our point of view, their atmospheres can filter the starlight lightly during transits, imprinting spectral hints of their chemical composition. This gives telescopes like the James Webb Space Telescope a chance to detect molecules such as water vapor, carbon dioxide, methane, and perhaps even ozone, substances that, on Earth, are entwined with biology. The relatively cool temperature and small size of TRAPPIST-1 help sharpen these signals. The contrast between the star and each transiting planet is greater than in hotter stellar systems, amplifying the delicate whisper of an atmosphere against a deeper tone of starlight. The alignment of factors here, multiple similar planets, close proximity to Earth, and favorable transit geometry, make this system a natural laboratory for the study of planetary atmospheres and life's possible footholds in the cosmos. In many ways, TRAPPIST-1 is a window into the diversity of planetary systems that our galaxy holds. It presents not just one, but 7 parallel possibilities. Each planet is a test case, a natural experiment in how geology, climate, chemistry, and possibly biology can unfold. Together, they form a rich comparative framework, allowing astronomers to refine their understanding of how planets become habitable and what signs of life we might one day detect. As our instruments grow more powerful, we step closer to answering one of the most profound questions we can ask. Are we alone? In this quiet corner of the galaxy, the TRAPPIST-1 system waits patiently, its 7 worlds turning in perfect time, holding their secrets in the silence between stars. Across the vastness of space, only 4.2 light-years from Earth, there lies a small planet, orbiting a faded ember of a star. This world, Proxima Centauri b, is the closest confirmed exoplanet to our solar system. It circles Proxima Centauri, a red dwarf star in the Alpha Centauri system, an age-worn stellar companion faintly visible in southern skies. Though the gap between us and this world sounds small on the cosmic scale, even light, moving at nearly 300,000 kilometers per second, takes years to make the journey. Proxima Centauri b is roughly the same size as Earth, and it resides within the so-called habitable zone of its star. This is the not too hot, not too cold band where liquid water could exist on a planet's surface, given the right atmospheric conditions. That possibility alone is enough to stir the scientific imagination, because water is one of the essential ingredients for life as we understand it. But this calm appearance conceals a challenge. Proxima Centauri is a red dwarf star, and although these stars are slow-burning and stable over trillions of years, they are also turbulent in their youth. They are prone to flares, powerful bursts of energetic radiation. Proxima Centauri has been observed releasing fierce storms of ultraviolet and X-rays, often orders of magnitude more intense than the flares seen from our own Sun. These storms could batter Proxima b routinely. The consequences of such flares for a nearby planet are profound. If Proxima b once had an atmosphere resembling Earth's, these eruptions may have stripped it away over time. Without a protective magnetic field or a dense blanket of gases, the volatile breath of the star would slowly bleed its shield into space, leaving the surface exposed to radiation and solar particles. And yet, the story may not be so simple. There are scenarios in which an atmosphere could survive. A thick atmosphere, perhaps 10 or more times the pressure of Earth's, could absorb the radiation. A strong planetary magnetic field, similar to the one generated deep inside Earth by its spinning molten core, might also deflect the worst of the stellar winds. Alternatively, if the planet is tidally locked, with one hemisphere always facing the star and the other shrouded in eternal night, a stable twilight zone along the terminator line might harbor temperate conditions. There, heat could balance just enough to allow water, if present, to remain liquid. And maybe, just maybe, life could find a place to cling on. Proxima b completes an orbit every 11 Earth days, hubbing its star at a fraction of Mercury's distance from the Sun. Yet despite this proximity, the planet receives only about 65% of the energy that Earth does. That is partly because Proxima Centauri is small, only about an eighth the mass of our Sun, and far dimmer. Life there, if it exists, would develop under ruddy skies. The light would fall across the surface, like late evening on Earth, with photosynthesis, if it occurs at all, adapting to the longer, redder wavelengths. Even now, astronomers are refining their models of Proxima b's orbit, mass, and potential composition. Observations from ground-based telescopes have strengthened our estimates of its size, while future missions may one day scan its atmosphere, if one exists, for the chemical fingerprints of life. Instruments like the James Webb Space Telescope will peer farther and finer, seeking out carbon dioxide, methane, or oxygen, molecules that, in the right balance, tell a compelling story of biology at work. Proxima Centauri b reminds us that the search for life is not only directed outward, but also inward, to the very conditions that allowed Earth to evolve and endure. In every rocky surface, in every stretch of atmospheric haze, we see fractured reflections of ourselves and measure the narrow margins that separate a barren rock from a living world. For now, Proxima b is a mystery in the dark, but it is also a promise. A neighboring world, hidden in the glow of another sun, waiting for the light of understanding to reach it. 40 light-years from Earth, in the constellation of Cetus, a planet orbits its faint red star with quiet determination. This is LHS 1140b, a super-Earth with a compelling list of qualities that attract the interest of scientists studying planetary habitability. It is rocky, like Earth, but more massive, weighing in at around 6.5 times the mass of our home world. This extra heft gives it a stronger gravitational pull and may allow it to hold onto a thick atmosphere over billions of years. The planet lies well within the habitable zone of its parent star, the region where temperatures could permit liquid water to exist on the surface. This red dwarf star is smaller and cooler than the Sun, but LHS 1140b moves through a closer orbit, balancing the energy it receives. Day by day, the warmth of its star bathes the planet in a light far less intense than daylight on Earth, but potentially sufficient to support the emergence of liquid water, clouds, and even weather systems. What sets LHS 1140b apart is more than its position in the habitable zone. Observations suggest it may possess a dense and stable atmosphere. Infrared measurements and other data hint at the presence of gases, such as carbon dioxide or even water vapor, though confirmation awaits more detailed analysis. If those early signals are correct, it means this world could maintain a greenhouse effect, gently trapping heat and creating surface temperatures conducive to life. This possibility becomes still more intriguing when we consider the planet's environment over time. Red dwarfs like its host star burn far less intensely than stars like the Sun, but live for far longer stretches of cosmic time. Although they can be tempestuous in their youth, producing flares and bursts of radiation, older red dwarfs settle into stability. The star LHS 1140 is thought to be relatively mature and calm. This tranquility gives any planetary atmosphere a better chance of surviving undisturbed, allowing complex chemistry to unfold across centuries and eons. Because LHS 1140b is larger and heavier than Earth, it may exhibit stronger volcanic activity. If so, it would replenish its atmosphere with gases released from the planet's interior. This cycle, volcanism, outgassing, and atmospheric renewal, is crucial for sustaining a climate that might one day support ocean-bearing landscapes or microbial life. The planet's gravity and potential atmospheric pressure also feed speculation about surface conditions. A higher pressure could keep water liquid over a broader range of temperatures. Lakes, rivers, or shallow seas, if they exist there, might be steamy or cloud-shrouded, but still capable of nurturing some form of biology. Even simple organisms, adapted to local conditions, would change the planet's story forever. We do not yet know what kind of world LHS 1140b truly is. Whether its land is barren or rich with alien terrain, whether its atmosphere carries oxygen or only carbon and nitrogen, remains a mystery. But it is large enough, warm enough, and long-lived enough to remain firmly on the short list of promising exoplanets. It is a reminder that Earth-like conditions could emerge in very different solar systems, under stars that glow dim red rather than brilliant white. Future telescopes, like the James Webb Space Telescope and others still on drawing boards, may soon begin to peel back the layers of this world's atmosphere, scanning for chemical signatures of life. In time, we may determine whether its skies are hazy or clear, whether clouds drift gently in cool winds, or whether light reflects off the surface of distant oceans. LHS 1140b remains out of reach, its secrets locked behind years of travel and layers of atmosphere. And yet, From across the gulf of interstellar space, we are learning to read its signs. It is a world that fits within our expanding map of possibility, a place where the conditions for life might not just survive, but flourish. 124 light-years away, in the constellation of Leo, a distant star shines softly in the darkness. And circling that star is a world unlike any in our own solar system. It is called K218b. This exoplanet has captured the imagination of scientists and stargazers alike, because it may harbor one of the most essential ingredients for life as we know it: water. K218b is large compared to Earth. It likely falls somewhere between a super-Earth and what astronomers call a mini Neptune. That means it may not be a rocky world like ours, but something more complex. Its mass is more than 8 times that of Earth, and yet it lies within its star's habitable zone, the region where temperatures could allow liquid water to exist on the surface of a world, assuming the atmospheric conditions are just right. In 2019, astronomers made an exciting detection. Using the Hubble Space Telescope, they found signatures of water vapor in the atmosphere of K218b. This doesn't mean oceans or rivers, not yet. But it does mean that water, in some form, is present. And in the search for life beyond Earth, water is always the first signpost we look for. The planet orbits a dim, cool red dwarf star. These stars are smaller and longer-lived than our Sun. They're also very common. Most of the stars in the Milky Way are red dwarfs. For K218b, this means a slower pace. Its year lasts just 33 Earth days, and yet it receives a similar amount of energy from its star as Earth receives from the Sun. Still, red dwarfs often produce stellar flares, bursts of radiation that could strip away atmospheres or damage life on nearby planets. And so, habitability remains an open question. The world itself is enigmatic. It may possess a deep gaseous envelope rich in hydrogen and helium. This boundary layer wraps around the planet like a heavy cloak, possibly hundreds of kilometers thick. Beneath this gaseous shroud, the pressure rises. Temperatures deepen, and somewhere far below, there could be a rocky core, perhaps an ocean, buried in darkness, insulated from the surface by thick clouds and gas. The presence of water vapor suggests that clouds or water cycle might exist in the upper atmosphere. But this world's thick atmosphere also poses a challenge. Hydrogen-rich envelopes like this can trap heat. They may create conditions closer to those seen on planets like Neptune than on Earth. Dense greenhouse layers could push surface temperatures well beyond the limits of known life. And even if an ocean does exist, the pressure may be too high, the chemistry too unfamiliar. Unlike Earth, K218b's environment is probably not home to blue skies or land masses. It may be an ocean world, or an ice-covered body below a steamy, cloud-filled sky. Floating within its atmosphere, between the extremes of heat and cold, exists a region of relative stability. Some have speculated that microbial life, if it ever arose, might survive in these temperate atmospheric layers, suspended in the vapor, drifting like plankton in the upper ocean of air. Such life would be radically different from anything seen on Earth. But the universe is vast, and life may not always follow familiar paths. Astrobiologists are beginning to expand the idea of habitability. No longer limited to Earth-like surfaces, they now peer into gas envelopes and ice shells, seeking energy, chemistry, and time. Future telescopes, including the James Webb Space Telescope, will peer more deeply into K218b's atmosphere. Infrared instruments could measure the composition of its clouds, hunt for other molecules, perhaps methane, carbon dioxide, or ammonia. Some of these gases might be clues, subtle hints of chemical disequilibrium that on Earth would point toward life. We are just beginning to learn the language of these distant atmospheres. K2-18b is a puzzle with pieces scattered across light years. And while it may not be another Earth, it invites us to think differently, to imagine forms of habitability shaped not by firm ground, but by thick vapors and elemental extremes. Even in mystery, K2-18b reminds us that water worlds may not be rare. They may, in fact, be common, and in them, perhaps, nature has found new ways to write the story of life. Gliese 667cc orbits a star that, in turn, dances its way through a triple star system some 24 light-years away in a constellation of Scorpius. Gliese 667cc is a red dwarf, cooler and dimmer than our Sun. Yet despite this modest output, the planet finds itself nestled within what we call the habitable zone, neither too hot nor too cold for liquid water to potentially pool on its surface. The planet is a super-Earth, meaning it is larger and more massive than Earth, but remains, in structure, likely to be rocky rather than gaseous. Estimates base its mass at around 4.5 times that of Earth. With this strength in gravity, it's possible the planet has retained a thick atmosphere, one capable of supporting the complex balance of fluids and gases necessary for habitability. But the details remain elusive. And herein lies the delicate art of inference. From the faint dimming of a star to the tug of its orbit, the presence of a triple star system adds a layer of orbital complexity and beauty. From the surface of Gliese 667cc, were you to stand on its rocky soil beneath a clear atmosphere, you might look up to see not one, but 3 suns casting various streams of light across the sky. Its primary sun, the one it orbits closely, would dominate the day. The 2 companions, Gliese 667a and b, would appear much smaller, perhaps like brilliant twin stars in the dusk or early morning, dancing across the horizon in slow celestial arcs. Their effect on the planet's climate and stability is deeply interesting. Multi-star systems can generate orbital instabilities, but in this case, the distances appear great enough to leave the planet's path largely undisturbed. For now. Gliese 667cc receives about 90% of the energy Earth does from the Sun. That balance is critical. Too little energy, and a planet freezes. Too much, and whatever water it may have once held evaporates away. But with an appropriate atmosphere, perhaps dense in carbon dioxide or water vapor, thick enough to capture and distribute heat, Gliese 667cc could maintain temperatures that allow oceans to exist, clouds to form, and perhaps even cycles, like those we know here on Earth, of rain, evaporation, and radiant sunlight filling the sky. On planets orbiting red dwarfs, there is often concern about tidal locking, where one hemisphere perpetually faces the star, while the other remains in darkness. In such cases, the danger is not in the stillness of the lands, but in the harsh divide, a scorched dayside and a frozen nightside. But here again, a thick atmosphere might come to the rescue, redistributing warmth from one hemisphere to the other. In fact, some models suggest such planets could host a stable terminator zone, a twilight ring where temperatures are moderate, perhaps allowing rivers to flow gently, and seasons to vary with tolerable rhythm. There is no direct evidence yet of an atmosphere, though astronomers continue to examine the data with growing precision. Instruments of the near future, spaceborne observatories hung far from Earth's interference, may soon have the resolution to sample the faint light that passes through this planet's atmosphere as it crosses in front of its star. That filtered starlight may reveal substances like oxygen, methane, or water vapor, molecules that don't merely hint at habitability, but suggest the tantalizing possibility of life. Of the hundreds of planets orbiting within habitable zones, this one stands as a frequent contender, not because we know it is Earth-like, but because everything we have observed so far suggests it could be. Not forbidding, not scorched or frozen beyond refuge, but temperate, gravitationally stable, and in many ways familiar. The path from possibility to certainty, however, is slow and careful. But it begins here, in distant light, numbers, and orbital lines traced across the sky. A pale world waiting in the quiet glow of 3 suns. TOI 700d drifts silently around its cool, calm star, a relatively unassuming red dwarf, over 100 light-years from Earth. This small, dim star might seem an unlikely host for an Earth-like planet. Yet, here we find one, the 3rd planet from its sun, in a system revealed by NASA's Transiting Exoplanet Survey Satellite, or TESS. It's roughly Earth-sized, and it sits precisely in its star's habitable zone, that narrow orbital band where temperatures may be just right for liquid water to exist. The discovery of TOI 700d is significant not because it is entirely unique, but because it combines several remarkable conditions into one quite hopeful world. In the past, many Earth-sized exoplanets have been found orbiting red dwarfs, which make up the vast majority of stars in our galaxy. These stars are small, cool, and relatively long-lived, meaning that their planets have great spans of time in which life could possibly evolve. But red dwarfs are often volatile. They tend to emit powerful stellar flares, eruptions of charged particles and radiation, strong enough to strip the atmospheres from any planets that orbit too close. Flares like these can pose one of the greatest threats to habitability. Even if a planet lies within the right distance for water, these explosions could sterilize the surface and leave no shelter for life as we know it. TOI 700d's parent star, however, is calm. Observations show unusually low stellar activity. It doesn't roar with the violent temper of its more energetic cousins. It fizzes gently in the dark, steady and peaceful. This stellar quietness is a gift. It increases the chances that TOI 700d could retain a stable atmosphere. And a stable atmosphere is key not only to holding onto water, but to shielding life from harmful radiation, nurturing climate cycles, and transporting the gases that may one day betray life's presence. The planet completes one orbit every 37 days. Because the host star is much dimmer than our Sun, even this close distance keeps it within a comfortably warm range. Any liquid water on the surface, if it exists, would stay unfrozen but not boil away. Models suggest TOI may be tidally locked, with one face always pointing toward its star, trapped in perpetual daylight, while the other lies in endless night. But atmospheric currents, if strong enough, could move heat from the lit side to the dark, creating only gentle gradients, perhaps even allowing for temperate conditions across large regions. We do not yet know whether TOI 700d truly has an atmosphere, or whether it possesses water. Telescopes like the James Webb Space Telescope are just beginning the work of sampling light that filters through distant exoplanet skies. In time, we may see the signatures of water vapor, or signs of carbon dioxide and methane, clues that could whisper of geological or even biological activity. The excitement around TOI 700d lies not only in its distance or its size, but in its quiet possibility. It is not battered by flares or squeezed by extreme gravity. It does not orbit in a raging young system filled with danger. It represents a kind of planetary peace, and in that peace there may dwell the conditions we believe life requires: liquid water, a protective sky, time to evolve, and a stable source of warmth. There is, of course, much more to learn, but in the growing catalogue of exoplanets, TOI 700d stands out as a quiet candidate with great promise. A world that may, one day, widen our understanding not only of where life can exist, but how frequently it may emerge across the galaxy. It is a reminder that habitable real estate may be more common than we ever imagined, hidden among the dim stars, shining steadily, waiting patiently to be known. Ross 128b lies just 11 light-years from Earth. In the scale of the cosmos, this is exceptionally close. It orbits a red dwarf star, a type of star smaller and cooler than our Sun. These stars are common across the galaxy, and many harbor planetary systems. What makes Ross 128b distinctive is where it sits in the cosmic theater. It resides within the so-called temperate zone, a region around its star where temperatures could allow liquid water to exist on its surface. Its star, Ross 128, is unusually quiet for a red dwarf. Most red dwarfs are known for violent stellar activity, but Ross 128 is different. It rotates slowly and produces relatively little magnetic disruption. This stability bodes well for the planet that circles it. Ross 128b completes a full orbit in just 9.5 Earth days. Given the close distance to its host star, one might expect the planet to be scorched, inhospitable. But red dwarfs are much cooler than stars like our own. This proximity places the planet snugly within the temperate zone, where it may receive just the right amount of energy, neither too much nor too little. It is likely tidally locked. This means the same side of the planet always faces its star, one hemisphere bathed in endless daylight, the other cloaked in perpetual night. On Earth, such a state would create extreme differences in temperature and climate. But if Ross 128b has a substantial atmosphere, dense enough to transfer heat from the day side to the night, then its surface might be more temperate than we expect. Winds could distribute warmth, moderating the planet's climate and allowing for more stable conditions across its surface. Mass estimates place Ross 128b at around the same mass as Earth, suggesting a rocky composition. This is a critical factor. Gas giants and ice worlds offer fewer footholds for life, at least as we understand it. But a rocky terrestrial planet at the right distance from a quiet star, this is the kind of place where researchers begin to talk about habitability with cautious optimism. We have not yet seen its atmosphere. That will take new instruments and new missions. But the path is clear. Future telescopes like the James Webb Space Telescope and the European Extremely Large Telescope will be able to study exoplanetary atmospheres in unprecedented detail. One day, they may even glimpse the spectral signatures of gases like oxygen, methane, or water vapor in the light from stars like Ross 128. Even now, this planet urges us to look deeper. The signal that first hinted at its presence came through radial velocity measurements, tiny wobbles in the motion of the parent star caused by the planet's gravity. From these hints and flickers, we piece together whole worlds. For Ross 128b, that means a place with Earth-like mass, orbiting in benign stellar conditions, in a location where temperatures might permit liquid water. This quiet world circles in darkness, its landscape unknown, its skies unseen. Yet it presents us with questions both ancient and profound. Could life rise on such a world? Has it already? Might it look like our own? Or might it be something stranger? Ross 128b is a scientific prospect, valuable, nearby, and ripe for study. It is also a reminder that our cosmic neighborhood holds more promise than we once imagined. just beyond our stellar doorstep, worlds like this await our attention. They call softly across the void, whispering of climates and histories alien to our own. But in these whispers lies a possibility, a chance that the universe may be more alive and more familiar than we ever dared to dream. In the quiet vastness of the night sky, where imagination meets scientific inquiry, a new era of discovery is beginning. The search for life beyond Earth is no longer confined to theory. We have found worlds that could support it, planets that orbit other stars with familiar traits, some rocky, some warm, some wrapped in atmospheres rich in mystery. But the next steps in this journey are about to unfold, with tools and missions designed not merely to imagine life elsewhere, but to detect its fingerprints. At the heart of this unfolding story stands the James Webb Space Telescope. Launched in December of 2021, it is the most powerful observatory ever placed in space. Webb can peer into the atmospheres of exoplanets with remarkable precision. Using a technique called transit spectroscopy, it watches as a planet passes in front of its star. In those moments, starlight filters through the planet's atmosphere. Molecules like water vapor, carbon dioxide, methane, and oxygen can imprint subtle signatures in that light. Biosignatures, perhaps, hints of life's chemistry, written in infrared. Webb is already probing worlds like K218b, examining the thick hydrogen-helium envelopes that shroud potential water layers, searching for disequilibrium in atmospheric chemistry. In nature, disequilibrium is often a sign of life. On Earth, for instance, the coexistence of oxygen and methane in our atmosphere is sustained by biology. Discovering such patterns on a distant planet would be one of the most profound achievements in science. But Webb is only the beginning. The European Space Agency is developing a mission called Ariel, the Atmospheric Remote Sensing Infrared Exoplanet Large Survey. Scheduled for launch by the end of this decade, it will study the atmospheres of hundreds of exoplanets, focusing on their chemical compositions, temperatures, and cloud dynamics. Ariel's systematic approach will help build a catalogue of planetary atmospheres across a diverse range of worlds, from scorching gas giants to temperate rocky planets. It will teach us about planetary formation, evolution, and the subtle conditions that could make a world habitable. Beyond Ariel lies an even more ambitious vision, LUVOIR, the Large UV Optical Infrared Surveyor, currently in conceptual stages. It is one of NASA's proposed flagship missions for the future. LUVOIR, if built, could be launched in the late 2030s or early 40s. Taller than a house, its enormous mirror would collect light with breathtaking sensitivity. LUVOIR could directly image Earth-like planets around nearby stars. No easy feat, given how faint such planets are, lost in the glare of their stars. But with the power of coronagraphs, or perhaps even starshades, LUVOIR could block the starlight and reveal the pale glow of another Earth. By dispersing this faint light into a spectrum, we could read the atmospheric composition of these worlds. If we find oxygen alongside methane, signs of photosynthesis or other metabolic processes, we may have glimpsed life. LUVOIR would not only mark a technological triumph, but also a philosophical breakthrough. It would ask questions once left to myth and poetry, and answer them with light. These missions, taken together, will redefine how we view the universe. For centuries, the idea of other inhabited worlds was a speculation. Then, with Kepler and TESS, we realized that planets are everywhere. Now, with Webb, Ariel, and LUVOIR, we are on the threshold of uncovering whether any of them are alive. They will also challenge our understanding of what makes a planet habitable. We may find that our current criteria, the presence of liquid water, the right temperature range, a stable atmosphere, are too narrow. Life could emerge under conditions yet unknown to us, or we may find that it is rare. that Earth is not just a pale blue dot, but a singular oasis in a mostly barren galaxy. One day, with enough data, patterns will emerge. We might learn that most life-bearing planets orbit quiet red dwarfs, or perhaps that only a narrow band of solar-type stars host worlds teeming with biology. These discoveries will demand new theories and ideas, and they will stir something ancient in us, the desire to know who and what we are in the great sweep of space and time. This is a moment of anticipation, the calm before revelation. If life has taken root elsewhere, we may soon see its reflection in a trembling beam of starlight.